My name is Nihar Perry, and I'm excited to share our recent work, Deep KNN Defense Against Clean Label Data Poisoning. First, I'd like to start by answering the question, what is clean label poisoning? Clean label poisoning has two properties. The images are visually unperturbed, and the ground truth label matches the content of the image. This means that the attacker does not need access to the data labeling function, allowing for large-scale poisoning attacks under white box, gray box, and black box scenarios. You can imagine a potential attack vector as follows. I'm interested in weakening your state-of-the-art ML system on a particular test time target image. Under the clean label attack paradigm, I only need to post a few poisoned images online, wait for them to be scraped by a bot, labeled by a human, and introduced into your training pipeline. Now I have a backdoor into your machine learning system. Most importantly, without any defensive procedures, it's nearly impossible to identify that your model has been compromised, since clean label poisons often preserve overall test accuracy. I'd like to focus on two particular clean label attacks. First, the feature collision attack crafts poisons, such that the poisoned images overlap with the target in feature space, causing misclassification. You can visualize this in the linear SVM case, where the shaded red poisons shift the decision boundary. Next, the convex polytope attack crafts poisons using a more complex optimization function to form a convex hull around the target in feature space, causing a misclassification. Convex polytope attacks are considered to be both stronger and harder to identify. With these two poisons in mind, I'd like to introduce our proposed defense based on K nearest neighbors. Particularly, we're interested in leveraging the deep features generated by a neural network to identify outliers by comparing each point in feature space with the mode of the ground truth labels in a point's neighborhood. As seen in the figure, the poisons are flagged as anomalous because they have different ground truth class labels than the surrounding points. A few important things to note here. First, the deep features used in this defense are derived from a pre-trained feature extractor. And second, the deep KNN defense acts as a pre-processing step, identifying and removing suspected poisons prior to training. Moving on to our evaluation results on CFAR10, we note that the deep KNN defense achieves the highest defense success rate compared with other simple baselines, while also filtering out the fewest number of clean images. The deep KNN defense works so well because it exploits the implicit spatial locality of poisoned images created by either the feature collision or convex polytope attacks. However, this also serves as the primary limitation of the defense. This method will likely not be able to filter poisons in two cases. First, if a significant number of poisons surround a target, the poisoned class is no longer an outlier in the neighborhood and is not removed. Additionally, more sophisticated adaptive attacks that craft poisons without the spatial locality property mentioned earlier will likely be able to circumvent this defense. Lastly, I'd like to talk about the deep KNN defense in the context of real-world applications. We study two important questions. We empirically identify the best way of choosing the size of the search neighborhood or the parameter K in the KNN defense, and the effect of class imbalance on the effectiveness of our outlier detection method. We find that searching a neighborhood 4 times as large as the size of your largest class leads to lower test accuracy. We also find that replicating data points as a form of augmentation for underrepresented classes effectively preserves test accuracy. A naive approach to the KNN algorithm is both memory intensive and computationally inefficient, particularly for large data sets. However, we can look to research an algorithm designed for GPU-based hardware optimizations, hashing strategies for fast lookup, and approximate nearest neighbor search for strong performance in a fraction of the time. The deep KNN defense is a simple yet robust approach that improves upon the simple baselines for clean label attacks and serves as a benchmark for future work in clean label poisoning. For more in-depth analysis, be sure to check out our full paper and code on GitHub. Thank you.